Welcome to The Explainer. Today, we're diving into a genuinely fascinating paradigm shift in artificial intelligence. We're going to unpack a dense, mathematically rigorous, but absolutely game-changing framework known as frequency-governed self-graph reasoning, or FGSGR for short. We're finally moving away from the massive, completely opaque black boxes of current AI and looking at a totally new, completely transparent way to architect intelligence.
Here's the roadmap for today. We'll start with the AI bandwidth wall, move into modular skill distillation, then look at math, graphs, not weights. After that, we'll cover the biological metacognitive grid and wrap things up with verified truth and containment. Let's get right into it. All right, section 1, the AI bandwidth wall and hitting the physical limits of edge computing. So we have to start by addressing the massive elephant in the room right now. Our current monolithic large language models, the giant LLMs we all know and use, they're literally hitting a physical wall. I mean, they're huge. They require massive power-hungry data centers, and you fundamentally cannot deploy them efficiently on small edge devices like a drone, a robot, or remote sensor. They rely on these bloated, dense matrices with massive parameter counts, and because everything is just mashed together, they are super prone to catastrophic forgetting, and of course, hallucinations. But FGSGR? It takes a completely different path. It basically ditches that giant global brain in favor of localized, sparse networks. By using explicit factor graphs, it guarantees logic and operates with just incredible efficiency. To put that efficiency into perspective, the entire FGSGR framework operates under a 2 GB parameter footprint. 2 gigs, that's tiny. And by utilizing structured 2 to 4 block sparsity, which is just a fancy way of saying half the values in any given matrix block are exactly 0, the active memory drops even further. This makes it absolutely perfect for highly constrained hardware, like say the NVIDIA Jetson or a Nano, while still leaving plenty of breathing room for dynamic, real-time execution. But listen, size isn't the only headache with standard AI. There's also this thing called the autoregressive probability dilution problem. In standard AI, generating a sequence is kind of like rolling dice over and over again. If there's a rare but perfectly correct logical deduction, the probability of the AI actually selecting that exact path drops exponentially with every single step. It's like eventually that valid edge case logic just gets completely washed out by generic high-probability semantic noise. Well, FGSIR mathematically prevents this. It throws out stochastic guessing entirely and maps the state space directly to a factor graph using hard, explicit algebraic constraints. So invalid paths literally just vanish, and those rare, valid edge cases, they are totally protected from that probability dilution. Which brings us to section 2, modular skill distillation. This is all about isolating expertise from the giant brain. To actually get that isolated expertise, FGSGR doesn't just train a massive model from scratch. Instead, it distills a giant AI teacher down into small, independent expert modules. And it does this using a very specific mathematical tool called forward KL divergence minimization. Now, instead of standard joint weight fine-tuning, which can frankly wreck the model's logic, this system uses forward KL because it's what we call mathematically zero avoiding. Basically, this means the lean student model is absolutely forced to maintain the full scope of the teacher's expert reasoning. It literally cannot drop those rare but critical edge case logical deductions just to save space. It is forced to remember them. And by applying this distillation, we can strip away all that conversational noise. The polite chatbot fluff that we don't really need. We're left with specific, high-fidelity, latent skill manifolds. We're breaking the intelligence down into independent expert subgraphs. So you end up with dedicated, highly tuned modules for code, physics, math, and logic. Think about it. You definitely don't need a billion-parameter model to solve a math problem if you have a perfectly distilled, pure math expert subgraph right at your fingertips. Moving right along to section 3, math, graphs not weights. We're trading opaque tensors for transparent logic. So, how do we actually run these distilled skills using deterministic math without relying on dense, opaque parameter weights? Well, to make sure these individual expert modules play nicely together without breaking each other, every single one is wrapped in what's called a Markov blanket. You can think of this like a mathematical anti-contamination shield. It forms a strict boundary that totally separates the internal logic of an expert from the rest of the system. This guarantees that if, say, one skill gets corrupted or hits some bad data, that error cannot logically cross-contaminate and infect the rest of the system's logic. It is literally the ultimate firewall for reasoning. Now, to think and actually verify itself, this framework uses a bidirectional cross-consistency loop. With standard LLMs, if you want to verify an answer, you have to generate a bunch of new text responses, right? Which is super slow and really expensive. But because FGSGR is structured as a graph, it runs a forward pass to reach a conclusion, and then instantly, and I mean instantly, runs a backward pass, an inversion, across that exact same topology. It's checking to see if the output structurally reconstructs the input causes. It analytically checks its own homework without generating a single new costly text token. Pretty brilliant, right?
And because this process uses what's called bounded message damping, the speed is just unreal. The entire system is mathematically guaranteed to securely close its real-time operational loop in under 50 milliseconds. 50 milliseconds. That is exactly the kind of deterministic, hyper-fast response you absolutely need if you're running robotics, drones, or physical actuators out in the real world.
All right, section 4, the biological metacognitive grid. Basically, AI with a pulse. This is where things get really fascinating. FGSGR doesn't just sit there running statically like your typical computer program. It effectively breathes. It scales its cognitive effort based on environmental stress, very much like a living organism. The architecture dynamically shifts between 5 quantized states depending on its cognitive load. It starts at state 1, this relaxed quiescent mode where it's just doing high-frequency self-cleaning and pruning redundant nodes. But if it encounters high uncertainty, boom, it instantly scales all the way up to state 5, emergency convergence. In that state, it locks its boundaries and forces maximum throughput to handle catastrophic logic spikes the moment they happen. It's dynamically allocating compute power exactly where and when it's needed.
Now, you might be wondering, okay, how does a decentralized system like this not just totally spin out of control? Well, stability across all those shifting states is absolutely guaranteed by a strict bounded message damping threshold. The system essentially locks its variation residuals below 10 to the negative 5th power. If the residual drops below that tiny, tiny number, the system has converged. This mathematically prevents the AI from getting stuck in those infinite divergent logical loops that crash other systems. And to manage all these crazy multimodal sensory streams pouring in from the real world, the system uses a 3D fast Fourier transform, or FFT, diagnostic router. Instead of relying on some sluggish AI classifier to figure out what a piece of data actually is, this router instantly stores complex thoughts like mixing math symbols and linguistics by their underlying frequencies. This ensures perfect contextual alignment, and it does it with zero copy latency. Which brings us to our final section, Section 5, Verified Truth and Containment, or Proving Logic Structurally.
Because look, at the end of the day, an AI is only as good as the truth of its reasoning, right? We need to know exactly how this framework verifies truth without keeping a human in the loop. We need an operational bridge from the old world of AI to the new. So here's how an LLM's messy, prose-based reasoning trace actually gets systematically converted into a typed, band-tagged knowledge graph. The system takes that raw reasoning, runs it through strict schema validation, builds a factor graph, and then calibrates it. In this system, confidence isn't just some self-reported hallucination. It's heavily calibrated and structurally verified against actual hard evidence.
And let me tell you, the structural verification defenses built into this pipeline are intense. The system rigorously guards against hallucinations by structurally verifying every single piece of the graph. It instantly rejects circular reasoning, so a claim can't just use itself as proof. It also detects convergent paths to make sure shared evidence isn't getting double-counted, because that would artificially inflate the AI's confidence. Basically, it replaces blind trust with explicit, auditable, probabilistic inference.
So what actually is truth in this framework? Well, in FGSGR, truth is defined as parsimony that persists, meaning if a small, hyper-efficient, disentangled graph can explain its environment perfectly using way fewer parameters than the original massive model, and without changing when you throw different test scenarios at it, then it has successfully distilled the structural truth out of those opaque AI weights. Truth isn't just what sounds plausible, it's the absolute simplest structural logic that holds up perfectly under pressure. Ultimately, though, the framework does acknowledge that no system is absolutely perfect entirely on its own. There's this irreducible trust floor, represented mathematically as rho times p. This is basically the product of a verifier's per judge error and the correlation between those judges. What this proves mathematically is that true safety requires model-diverse checkers. You literally have to lower the shared blind spots, the correlation, in your verification process to get that trust floor as incredibly close to zero as possible.
So, I'm going to leave you with this final thought to take away from our explainer today. As we look toward the horizon of artificial intelligence, does the path to artificial general intelligence truly require increasingly massive, power-hungry models that act as these impenetrable black boxes? Or does it simply require a biological, highly structured, and totally verifiable way to organize the parameters we already have? The FGSGR framework makes an incredibly strong case that it's the latter. Thanks so much for joining me on this deep dive, and I'll catch you next time.